Hey, you guys ready for video number 10, or technically 9B, I guess, since we had to do the titration of a weak acid by a strong base in two parts because the calculations are so long. So this is part 2. So in part 1, we did the volume required of the sodium hydroxide. We're reacting sodium hydroxide as our base titrant with the HNO2, the weak acid, in our flask. 50.00 milliliters of the acid, 0.1000 molar of both the acid and the base. So pretty straightforward numbers. So we did the volume at the equivalence point, which was 50.00 milliliters of the base. We did the initial pH of the HNO2. We did a pre-equivalence point at 49 milliliters, 1 milliliter before, right before the equivalence point. That was the buffer region. We did the half equivalence point, right? We did all that fun stuff. So we are now at the equivalence point. So we did the volume, the initial, the pre-equivalence, half equivalence. So we're number 5 now. Only 2 left, number 5 and 6. What's the pH at the equivalence point, which is much more challenging than when we did the strong acid, strong base. Strong acid, strong base, pH was 7 because the salt you formed was neutral. Not true, unfortunately, when you're titrating a weak acid with a strong base or a weak base with a strong acid. What you form is no longer neutral, so the pH at the equivalent point is not going to be 7. Post-equivalence point will be easy, but here at the equivalence point, we're adding equivalent numbers, the same number of equivalents of acid and base. So there'll be none of this left. So that'll be gone. That'll be gone. Right? They get wiped out. We're going to form these. So this we know is neutral. We don't have to worry about that. That gives an hydronium of 10 times minus 7, so we can ignore that. But the sodium hydroxide is a soluble salt, right? That forms a cation and an anion. So we've got Na plus and NO2 minus. So at any equivalent point where you're calculating the pH, you have to look at what exists. What are the principal species? So we've got sodium ions, but the sodium comes from a strong base. So this is neutral. I'm not worried about the sodium. But the NO2 minus, that's the conjugate base of a weak acid. Oh no. Oh no, they say. So if that's a conjugate base, that means the pH at the equivalence point should be greater than 7. Now we're going to calculate what that is, but we've got the presence of a conjugate base. So 2 parts of this. 3. 1, what the heck do we have? 2, how much of this formed? All right, so we need to figure that out. So let's figure out how much NO2 minus formed using neutralization stoichiometry. It'll be based off, they both run out at the same time, so we can figure out, well, the millimoles of this to start with is the millimoles of that formed divided by the total volume. So pretty easy to get the concentration of the NO2 minus. Then we have to set up the ice table. So very similar to the initial pH, but the initial pH was the weak acid only. The equivalence point is the weak base, NO2 minus. So we'll set up the ice table, show that forming OH minus, solve for X. X is OH minus. You're off to the races to get pH from them. So let's walk through those steps. Let's figure out the concentration of NO2 minus. If you feel like jumping at it, go for it while I erase my board. But I think this is the most involved calculation of them all for this type of titration. Did you get the concentration of NO2 minus? Let's take a look. So you can start with either the acid or the base, doesn't matter, because the same number of millimoles is going to react. So let's just start with the acid. And technically, I'd already calculated millimoles of acid, so I could have shortened this. I could have just gone back to part 2, I think, where we calculated the initial millimoles of acid and just started with that, right? And so we have 15.00 milliliters of the acid. 0.1000 millimoles per milliliter gives us that 5.000 millimoles of HNO2. You could have started with that. Well, 1 millimole of the acid produces 1 millimole of NaNO2. And then 1 millimole of NaNO2 contains 1 millimole of nitrite ions. you could do that in your head. So very easily, you could have just started with the 5.000 millimoles, understood it was a 1-to-1 ratio, understood that, and just gone, NO2 minus is going to be the same as that. You can be a little bit quicker if it's obvious for you on titrations. Well, we got 5.000 millimoles of NO2 minus that forms, as we didn't start with any, right? So we're going to get that based on what has been reacted on our left-hand side. Well, what's the total volume? Well, we had originally 50.00 milliliters of the HNO2, our weak acid. And if you go back to part 1, where we calculated the volume of base added to hit the equivalence point, we can use that now. We need that as a reference point for pre and post equivalence, but we need it to do this problem because that was 50.00 milliliters because they're the same concentration. So if I add those two together to 2 decimals, I get 100.00 milliliters total between the acid and the base. So to get the concentration of the conjugate base form, the NO2 minus, the nitrite ion, I take the millimoles of it formed, which is the 5.000 millimoles, divided by the total volume after everything got dumped in that flask, 100.00 milliliters. Go to 4 sig figs, I get 0.05000 molar. Nice, a nice simple number there. Now, let's take that, set up an ice table, solve for X. X will be OH minus. So do me a favor, set up the equilibrium equation for NO2 minus, all right? Ionizing in water, forming OH minus, and then do your I, C, and E ice table for me. So we are now back to the exact same problem we did in part 2, where we did the pH of the weak acid, HNO2. It's just took an extra step to figure out its concentration after the neutralization. Have at it! All right, here's your ionization equation. So everything's gone except for water, sodium ions, which are neutral, and nitrite ions, which are a weak base. So they're going to ionize in water. So we're just starting it fresh, forming OH minus and HNO2. 0.05000 molar of that to start with. We're assuming none of those. It's like a fresh new problem. Well, Q is obviously going to be 0, right? So Q equals 0. That's less than K. So that's going to shift to the right, pretty obvious. So I'm going to lose X of my starting weak base. I'm going to gain X of the hydroxide ion and gain X of the conjugate acid. So the equilibrium, 0.05000 minus X. 0 plus X is X, 0 plus X is X. It's the exact same format as we did in the step 2 with the weak acid, just in reverse. This is a little harder because we're not going to find the Kb value for NO2 minus. No! Are you ready? Let's solve for Kb. We're going to need it. We can't find it. Now remember, Kw is Ka times Kb. You will not find NO2 minus on your Kb table. Do you see the nitrite ion anywhere? No! Those are all amines, right? Ammonia and ammonia derivatives. So it is not on the table. So Kb not on table. So what we're going to do is rearrange this. So Kb will be Kw over Ka of the conjugate form, HNO2. We do know the Ka value for that. So remember Kw, 1.00 times 10 to the minus 14th. Let's look up the Ka. We have it written down earlier. So Ka for HNO2. And what was that, 7.2 times 10 minus 4th or something like that? Where's nitrous? There it is. Yep, 7.2 times 10 to the minus 4. Let's put that down. 3 sig figs, 2 sig figs. So if we punch that baby out, we should be able to get the Kb value. Where's my trusty calculator? Let's punch this in. So 1.00 second function EE negative 14 divided by 7.2 second function EE negative 4. Oh, equals 1.388888888 times 10 to the minus 11. So let's go to 2 sig figs here. 1.388, 1.3 vertical dash line, 88 times 10 to the minus 11. That's what my calculator says. Not that you can see it with the the sunlight creeping in. It's getting, when the afternoon the sun comes this way and I can't do videos anymore because it just reflects off the board. If I put the blinds down, it's too dark. So got a limited span of time I can do videos in this spot. All right, 1.388 times 10 minus 11. Now we have KB. We should be able to set up our equilibrium expression. Let's do that. There we go. So KB is going to be OH minus raised to the power of 1 times HNO2 raised to the power of 1 over NO2 minus raised to the power of 1. Don't include water because it's a liquid, condensed phase. What's OH minus? That's X. What's HNO2? That's X. This will be 0.05000 minus X. Yes. Let's make the assumption that X is really small. So this would be X squared over 0.05000. Right? And that'll equal KB. So X will just be the square root of the KB times the 0.05000 molar. Pretty standard procedure. Let's make sure that that's a valid assumption. So let's test it. Let's take the molarity of the base over KB. And again, two ways you can do it. You can solve for X divided by 0.05000 times 100. Hopefully that's less than 5%. Or just take the molarity times divided by KB. Hopefully that's greater than 100. We were barely, when we did the original acid, it was barely over 100. What's the molarity? 0.05000. KB, 1.388 times 10 to the minus 11. Something tells me this is going to be a little bigger than 100, like a lot bigger. 0.05000 divided by 1.388. Second function, EE, negative 11. Holy moly, that's a big number. So that's 3.602 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. I'd say that's a little bit greater than 100, wouldn't you? This is like totally valid, dude. So I'm pretty safe in assuming X is going to be super tiny. Therefore, X, which is OH minus, will just be the square root of KB times the initial concentration. Solve for X for me before I do the next board. And then take the negative log of that. That would be POH. Subtract that from 14. You get your pH, my friends. That's how you do it. The tricky part of the equivalence point is what you form is your product only, and then that is a conjugate base. So you got to set up a new ice table, but you don't know what KB is. You got to figure out KB yourself. All right, finish it up before I do. All right, so I rewrote our KB expression, solve for X. So take KB times the initial concentration, and I got 8.330 times 10 to the minus 7th molar. Good to two significant figures for our KB value. All right, well, from our ice table, that's what X is, right? That's OH minus. So POH is just negative log of that. So let's take the negative log of 8.330 times 10 to the minus 7. Two significant digits will give us two decimal places, right? So whatever that term of X is, the number sig figs determines the number of decimal places. Like a broken record around and around. I get 6.0793, good to two decimal places. But again, watch out. Red flag, that's not the pH, that's the POH. Remember, this is the conjugate base of a weak acid. NO2 minus is basic. It should have a pH greater than 7. That's not. That should be a warning. Make sure your answers make sense, okay? So pH plus POH is 14.00. Therefore, our pH will be 14.00 minus our POH, or our 6.0793. Two decimals, so I get a pH of 7.9207. Round that to two decimal places, you get a pH of 7.92. Now that is above 7, so that is slightly basic. That matches. That makes sense to me because the NO2 minus is weakly basic. There you go. So a strong acid, strong base is truly neutral at 7, but a weak acid titrated by a strong base, you'll have a pH a little bit greater than 7, depending on the identity and concentration of the conjugate base formed. We got one more step to do. Let's do a post-equivalence point. Let's do it after 50 milliliters. Here we go. If you look back to the prior problem, the prior video with the strong acid, strong base, any post-equivalence point, pH is exactly the same type of calculation, because it doesn't matter what the identity of the acid is or whether it was strong or weak. It doesn't matter because it's gone. All that's left is the titrant because we have excess titrant. So what's the identity of the titrant? In this case, sodium hydroxide. It's a strong base. So we're just going to have leftover strong base. So do the neutralization stoichiometry, figure out how much of that strong base is left, and you're off to the races. Exact same calculation as we did before. So the titration curve looks exactly the same in the post-equivalence region for both weak and strong acid titrations. So we want anything in that post-equivalence region, and remember it was 50.00 milliliters to hit the equivalence point of added base. So anything past that, so let's say 51.00. Let's go 1 milliliter, which you would never do in lab. You want like a half a drop. What is the pH after 51.00 milliliters of your titrant, your sodium hydroxide, has been added? Ideally, we'd do one maybe another 10 or 15 milliliters down the road if we had extra time to make a really nice graph. But we're just kind of scratching at initial equivalence points, somewhere pre-equivalence, tight up against the equivalence point, one tight up after it to get the rise of that S curve. And we can do the half equivalence points pretty straightforward. So what I want you to do here, use neutralization exactly like we did before. Calculate the amount of base left over because all the acid is gone. Correct? So all acid is gone. It is bye-bye. So we have left over, if I could spell, we have only sodium hydroxide left over. Now, some of you smarty passes there might be going, but don't you have the conjugate base as well? You have the sodium nitrite like we did for the equivalence point, NaNO2. Oh, that's a valid question. The NO2 minus formed is itself a weak base, and that's what determined the pH at the equivalence point, because we had no sodium hydroxide left at the equivalence point, right? It was gone. But remember what happens when you have, and we did this in one of the earlier videos, if you have a mixture of a strong base with a mixture of a weak base, you can ignore the contribution of OH minus from the weak base. The OH minus coming from the NO2 minus form is irrelevant compared to the strong base because it ionizes 100%. That's why we can ignore the autoionization of water. So the contribution from water, the contribution from the weak base, forget it, forget about it. Let's just do the strong base. Same thing's true with acids. If I have a strong acid with a weak acid, ignore the weak acid. It's irrelevant. The amount of hydronium it gives is pathetic compared to the amount from the 100% ionized strong acid. So good question, by the way. We have multiple sources of OH minus, but this is the only one that matters. So calculate how much is left over. I'll give you a moment to do that. This is as far as I could get on my little tiny board here. Look how tiny the board is. Let's squish your head. All right, anyway, I'm very highly mature, and you can still get a PhD. All right, here we go. All the acid's gone. We added extra base. So the initial millimoles of acid we added, we did back in step 2, right? So you don't have to recalculate it. We had 5.000 millimoles of HNO2 that we started with in our little flask. Already pre-calculated, so just rewrite it. That's from step 2. Well, how much base are we added? Same calculation as step 2. Take the volume, 51.00 milliliters of base solution, times its concentration, 0.1000 millimoles per milliliter. That gives us 5.100 millimoles of base added. Notice that is more than the acid. So the acid's the limiting reactant. Boom! Acid goes bye-bye. Subtract those. So 5.100 millimoles minus 5.00 millimoles, right? Now the base we had minus the amount of acid that was there. That's the millimoles of sodium hydroxide left over, which is, to 3 decimal places, 0.100 millimoles of sodium hydroxide left over. So let's calculate the total volume, volume acid plus volume base. Take the millimoles of the base left over, divided by the volume, and that's your concentration. From there, we can get pH quite readily. We're so close. And then in the next video, we're going to do exactly the same thing again, but we're going to titrate a weak base with a strong acid. It's going to be exactly the same, just mirror image. Oh, the pain. It's not so bad, it's just lots of work. What'd you get? What'd you get? What'd you get? Let's take our volume total. So 50 milliliters of acid plus 51.00 milliliters of base gives us 101.00 milliliters total of solution we dumped in that flask. That flask is getting pretty full. And if we're doing that titration, we've just been spraying it down with DI water. we have 0.100 millimoles of sodium hydroxide left, correct? Let's divide that by the 101.00 milliliters of solution because of the dilution. There was dilution on the solution. Gives me 9.9009 times 10 to the minus 4th molar, good to 3 significant figures. That's the sodium hydroxide concentration left over after the neutralization. Well, because the 1-to-1 ratio in a strong acid is 100% ionized, that would be the OH minus concentration. Let's take the negative log of that. So negative log of the OH minus, negative log of 9.9009 times 10 to the minus 4th is 3 sig figs, gives us 3 decimal places, 3.00432. That is the POH. Subtract that from 14. Remember, pH plus POH is 14.00. So you can always interconvert between pH and POH. So if I take 14.00 minus the POH of 3.00432, I'm limited to 2 decimal places here. Gives me 10.9956, which rounds to 2 decimal places of 11.00. Of course, that's way up there in the strong base category, and that'll slowly creep up over time, hitting probably into the 12, maybe even the 13 range after another 20, 30, 40 milliliters. Let's draw a titration curve. We're done with this problem and this video. How's your titration curve looking? All right, I just went from 1 to 12 on my y-axis and 0 to 100 on my x-axis for my base titrant volume. Initial pH, 2.07 at 0 mils. Half equivalence point at 25 milliliters of base was 3.14. Just before the equivalence point at 49 milliliters, right before it, we were right up here, 4 something. I forget exactly what that was. The equivalence point pH was slightly basic because of the presence of the NO2 minus conjugate base. That was a 7.92. Just eyeballing it here. And then a milliliter past it, it was about 10.9711, something like that. So you can see it still has that steep rise, but see a strong acid started about here. It has a much steeper rise. So the available indicators are fewer for a weak acid strong base titration than a strong acid strong base titration because the steepness isn't quite there. And then once we're past that equivalence point, it'll just, if we keep adding base, the pH will gradually go up. But that looks exactly the same as the strong acid strong base. So we can look between maybe about a pH 5 to 9-ish, somewhere in that range. It was much broader for the strong species. So any indicator that has its 2 pH range that our eyes can see, that falls between about 5 and 9, probably would be a good guess. So if you take a look at your indicators, so pH 5 is about here to 9, so we're talking in this range right here. Right, so anything starting here, so that you got this yellow to red, you got yellow to blue there, yellow to blue. Phenolphthalein might even work for that one pretty well. Yeah, probably good. Yep, see colorless to that. So phenolphthalein is usually the best choice. But we could pick the thymol blue, the phenol red, anything that changes in that range, you're good to go. Pretty hard to screw up that problem if I say, well, what indicator would you pick? Well, just any one of those that falls in that range, and you're awesome. All right, we only have a little bit left to go, and we're done for the semester. So we're going to do this exact same thing. It's long and exhausting, but we'll do it where it'll be the inverse of this, where we're going to start with a weak base and work backwards like an inverse S-curve. I'm only going to do that once for you guys. All right, and remember, I'm not going to ask you the whole thing on an exam. You might be overwhelmed, but I could say, what's the pH at just the equivalence point? Or just the half equivalence point, or anywhere in the pre-equivalence region where you got a buffer. And all of this is principles from the beginning of this chapter when we talked about buffers and the common ion effect, right? And things when we looked at acids and bases and ice tables. Nothing new at all, just applied concepts. Keep rocking, gang. You're almost there. You're to the finish line. Sprint to the end.